Hey there, AP Environmental Science class. Okay, we are now going to start Chapter 11, Geology, Soil and Mineral Resources. We're back to about 60 or so slides, so we're back to a two-parter here, not going to be a three-parter like Chapter 10, so there will be two parts, and Part 1 is going to start now. So again, Chapter 11, Geology, Soil and Mineral Resources. Okay, so we start off with a core case study. The real cost of gold. So, as you notice, we're going to be talking about some mining in this chapter. Those are our mineral resources. So the harmful effects of gold mining, massive amounts of rocks have to be dug out to yield only a small amount of gold. Highly toxic cyanide salts are actually used to extract the gold into settling ponds, and this cyanide or these cyanide salts are toxic to birds and mammals. They also can threaten underground drinking water supplies if the salts actually seep through the settling ponds and into any groundwater. And in 2000, a Romanian gold mine actually dam collapsed, and this contaminated rivers with the cyanide and the toxic metals. So again, when we look at the cost of gold, we don't factor in the full cost pricing, the environmental harm that mining for gold actually does for us. So using that as a little bit of an appetite to kind of whet our appetite as to what we're going to learn in this chapter, we start off with what are Earth's major geological processes, mineral resources. So this is going to go back to your Earth science days a little bit. Dynamic processes within the Earth and on its surface produce the mineral resources that we have. Mineral resources are non-renewable. Why? Because they're produced and renewed over millions of years, mostly by the Earth's rock cycle. So again, if something can be renewed in, let's say, a person's lifetime, we call it a renewable resources, like timber, right? Forests can grow within 100, 200 years. However, mineral resources like oil, we consider non-renewable because it takes over millions of years to actually produce and renew them. So we say that our mineral resources are going to be a non-renewable resource. So the Earth is a dynamic planet. Some terms to know about. Geology. What is geology? Well, it's the study of the dynamic processes taking place on the Earth's surface and in the Earth's interior. There are three major zones of Earth. You guys, again, should remember this from your Earth science days and even down into your middle school. We have the core. We have the mantle, which includes the asthenosphere. And if you remember the asthenosphere, we call the plastic mantle because that's where the plates float on top of, or we believe that happens. And again, remember the core has two parts, the inner core, which is solid, and the outer core, which is a liquid. Again, then the mantle, including the asthenosphere. And then we have the crust, two types of crust, continental crust and oceanic crust. And 71% of Earth's crust is actually classified as oceanic crust. Here are timescales for major geological and biological changes since the Earth formed 4.6 billion years ago. So again, just kind of going through, starting at the most recent is actually at the top here, the most distant at the bottom there, your Precambrian era. All right, first animals in the sea like jellyfish, first multi-cell organisms. Then we went to the Paleozoic, the age of the fishes. You'll notice a couple of mass extinctions that happened in that era. Then the Mesozoic, the age of the reptiles, a couple of mass extinctions, and now the Cenozoic, which is the age of the mammals that we are in now. And again, we're likely in that new mass extinction that we're talking about currently because of all the species that are going extinct. Again, we spoke about that in previous chapters. So once again here, I would look at this chart. I would definitely understand and have a few things memorized, errors that certain things happened in. Again, you're not going to have to totally memorize this entire chart, but definitely have a decent idea of what's going on here, just in case you need to use some of that information on a test or on an FRQ. So last, we take a look at this picture. Again, Earth is a dynamic planet. What do we have going on? Again, that inner core, the outer core. We have the asthenosphere, and we have where we're thinking the plates float on top of that. And then we have these convective cells with hot magma rising, cool magma then sinking, and we think that it's these convective cells in the asthenosphere manosphere in the mantle up into the crust that actually push plates aside and actually help move our plates across the Earth. So you'll notice that it looks up there, you'll see plate movement to the right, to the left there, again, as these convective cells work in the mantle, which again, hot magma rises, cool magma sinks, etc., etc., and it's that dynamic planet that is producing the plates to move around. That then produces earthquakes, volcanoes, things like that, which help produce the mineral resources that we're going to be talking about. So what are minerals and rocks? Well, minerals are a naturally occurring chemical element or compound that exists as a crystalline solid. What is a mineral resource? It's a concentration of minerals that we can extract and process into raw materials. And once again, our mineral resources are considered non-renewable resources. What's a rock? Well, a rock is a solid combination of one or more minerals. Okay, so that's what we talk about, the difference between a mineral and a rock. Minerals are basically the building blocks of your rocks. And we have our three types of rocks. Again, thinking back to earth science. First type, sedimentary rocks. Sedimentary rocks are made from sediments, dead plant and animal remains as well, or tiny particles of weathered and eroded rock. Those tiny particles, usually sedimentary rock is produced in some kind of water. As these particles fall out of the water, they settle, and then over time they compact and condense, right? A cementation occurs with those particles, or the dead plant animal remains, and then eventually you have a rock that forms, a layered rock, and we call that a sedimentary rock, and most of your fossils are found in sedimentary rock. Igneous rock forms under intense heat and pressure, so pretty much in a volcano, lava, for instance, is a type of igneous rock that then cools into a rock. Obviously, lava is the liquid form. Okay, so that's your igneous rock, usually forming from volcanoes. And then metamorphic rock is when you take existing rock and subject it to high temperature, pressure, fluids, or a combination of that, basically changing the rock or metamorphosizing the rock into something else. So igneous rock is basically lava or magma that cools. Metamorphic rock is some other type of rock, either sedimentary or igneous, that changes because of high temperature, pressure, fluids, or a combination of all of that, all three. Okay, so again, just have a general understanding of your three types of rocks as we head through this unit. We do also have the rock cycle. So Earth's rocks are recycled, but very slowly. That's why we call mineral resources a non-renewable resources. Remember the rock cycle. Rocks are recycled over millions of years. Erosion, melting, and metamorphism allows these rocks to change into something else, or to cycle. And it's the slowest of Earth's cycle processes. Again, the rock cycle taking millions and millions of years to complete. And here is the rock cycle. So once again, we'll start with sedimentary rock. Again, you have erosion, transportation, deposition of sediments. Then again, the rock solidifies together, your sedimentary rock. Then if you get some heat, pressure, or stress on that rock, it forms a metamorphic rock, which can then be weathered down to form another sedimentary rock, or could be melted into magma and then cools. And then you have your igneous rock, which again could be subject to heat and pressure and become a metamorphic rock, or could weather, erode, and be deposited and turn back into a sedimentary rock. So again, all this kind of combined here, all these rocks can change to one form to another. And again, that is our dynamic planet, our rock cycle. But again, non-renewable mineral resources, because this rock cycle takes millions of years to complete. All right, next we're going to talk about soil. So what processes lead to soil formations? Physical, chemical, and biological processes all contribute to the formation of soil. Soil is a renewable resource and a key factor in nutrient cycling. So soil, unlike minerals, is a renewable resource. And in fact, in my backyard, I have a mulch pile where I put my leaves and my grass clippings and things like that. And every year I get some new rich soil that is formed from the decaying or from the decay of that those leaves and the grass clippings and etc. As they get decayed, right? As our bacteria and our microorganisms decay it, they turn it into very nutrient soil. And again, this is a key factor in our nutrient cycling. So soil begins from bedrock. Again, hopefully you remember some of this from your earth science days. The process of weathering begins to break up parent material. That is the foundation of soil. Lichens then secrete acid that break down rock, the first step in primary succession. So remember back to our primary and secondary succession. Again, we said primary succession starts when there is no soil, when there's just bare rock. So what happens? Again, the weathering begins to break up the rock. Lichens, which are little organisms that sit, they're plant organisms, they're not real plants, but they look like it. They sit on the acid and they sit on the rock, and they have acid in them that actually begins to break down the rock. Then you have something called humus, that is formed. It's not hummus. Hummus is what you eat made of chickpeas that you kind of spread on stuff. This is humus. Humus is formed from dead organic material, releasing nutrients and holding moisture, physical, chemical, and biological processes, again, forming the soil. So understand this picture here, all right? Again, this is not only, we looked at this a little bit when we looked at primary succession, but this also is how soil is formed. So you'll notice in mature soil, you just have bedrock. You have the moss and lichens on top of the bedrock, right, beginning to break up the bedrock, weathering as well. Rain, wind, things like that will begin to break it up. Then you get young soil, all right, which has some organic debris on top, and as a result, you can get some grasses and small shrubs to grow there. And then eventually you have your mature soil with, again, our different horizons. If you remember from earth science, the O horizon, the A horizon, the B horizon, and the C horizon. We'll look at those more in a bit. And again, the top layer there, that's where your humus is. That's where all the fertile soil is located. And then obviously you get trees and ferns and other plants and animals to begin to use the soil that again turns into a mature soil. So again, soil is that renewable resource, so do have a general understanding on how it forms. Living organisms rely on soil. It's essential for agriculture. It provides the medium for growing timber and provides ecological services such as purifying water and degrading waste. So soil is a renewable resource and is natural capital, right? Soil produces ecosystem services and ecological services for us. So mature soils contain those horizons I mentioned briefly that were on that chart on the previous slide. Again, the O horizon is the leaf litter. That's basically the top where you have the leaves fall and branches are and things like that. Then you have A horizon, which is your topsoil, your B horizon, which is your subsoil, which is basically just things from the topsoil that have leached down or with rain, water has infiltrated and brought some of the topsoil down into the subsoil. And then the C horizon is basically the weathered parent material. So that's where the bedrock is that we started the process with, that weathered bedrock. Once the mature soil shows up, that bedrock is way down at the bottom with, again, the subsoil, the topsoil, and the leaf litter on top of that. So again, looking back at our chart here, that kind of goes through it. There's your O horizon, the leaf litter. There's your topsoil, your subsoil, and then again, your parent material, your C horizon there on the bottom. Okay, so once again, soil renewable resource. We have some natural capital, soil profiles of the principal soil types, typically found in 5 types of terrestrial ecosystems. So again, not only does the soil form from the rock and then the lichens, and then we get into the mature soil, but the climate of an area is also going to determine the type of soil you get. So you'll notice desert soil here is going to be different, right? They have a weak humus mineral mixture. They don't have as much organic material in the topsoil there, in the leaf litter. So desert soil maybe not going to be as nutrient rich as, let's say, a coniferous forest or let's say a deciduous forest. rainforest, right, where they have a lot of humus, because a lot of that, those leaves and stuff that fall end up turning into very nutrient soil. Again, here's your tropical rainforest. Again, they have acidic, light-colored humus. There's your coniferous forest. Again, grassland soil. All right, alkaline, dark, and rich in humus. So again, you have different climates are going to provide us with different soils, and then again, these different soils will have different nutrient capacities with them depending on the climate where they form. Again, you'll notice desert, not a lot of humus because there's not a lot of organic material. When you get into stuff like deciduous forest and grasslands where you have a lot of organic material, then you're going to have more of that humus layer. So again, things to think about. Definitely understand that climate controls the type of soil you're going to have, and definitely understand at least these five principal soil components here are in our 5 terrestrial ecosystems, at least our 5 main terrestrial ecosystems here. And again, several factors influence the formation of soil. Warm and wet environments will form soil faster. Again, compare the desert to us here in Ardsley, the deciduous forest. Again, I can get soil pretty much year after year, new soil. In a desert environment, that's not going to happen as quickly. Tropical rainforest soils actually have little organic material in the soil and are nutrient poor. So something to think about. Tropical rainforests, while you would think that they have a lot of nutrient-rich soil, actually don't, because most of the organic material is actually up in the canopy, right? Not a lot of organisms are living on the bottom of a tropical rainforest because you can't get any light down to the bottom. So believe it or not, their soils have little organic material and are actually nutrient poor. So definitely keep that in the back of your mind, because it's different than what you would think. You would think tropical rainforests have very nutrient soil. That is not the case. Their soil is actually poor in nutrients. So what is the importance of these soil nutrients? Well, again, you could probably imagine without these nutrients in the soil, we're not going to get agriculture, we're not going to get trees to form, we're not going to get all the things that the soil provides us. So most nutrients are in the A and the O horizons, right? We said that right up at the top in the leaf litter, or in that what we call the topsoil. That's where the humus is, all right, which is that rich black, very fertile soil that comes from a decayed organic material. Fertile soil produces high crop yields with this topsoil and bacteria that convert nitrogen into ions that plants can assimilate. So remember back a couple of chapters ago, right, back to that nitrogen cycle that helps cycle those nutrients. Again, fertile soil is going to have a lot of bacteria that will convert these nitrogen into ions that then the plants can use. The B and C horizons contain most of the soil's inorganic material. So again, that has leached down, or at least as the rain infiltrates and washes things down through the horizons, by the time you get to the B and C horizon, most of the nutrients have been left up in the A and O horizons, and what you're left with are is the inorganic material. And the soil texture determines its porosity and permeability. These are going to be words again from earth science. Porosity is how much airspace there is between soil grains, and permeability is how fast water is allowed to infiltrate or flow through the soil. All right, so those are important characteristics of soil: porosity and permeability. So looking at, again, what we're looking at here, this is permeability. Again, how fast water can flow through something, and obviously nutrients or soil that has big particles in it will be more permeable or highly permeable to water compared to soil that is rather small. Rather small soil will have low permeability. And this is important because you don't want your water to rush out, right, of your soil. If you have soil that allows water to just, infiltrate and then just wash right through, well, then unfortunately that soil is probably going to be dry a lot, and it might be harder to sustain plant growth. You want some water to hold in the soil so that the plants can use it. So again, you would want something, you would want your soil to maybe have a little bit of these smaller particles with it. But again, that being said, you also don't want to oversaturate your soil either. So you kind of want to have kind of in the middle here. You want to have soil that can allow some water to get out, but also holds some water so that the plants can use. So the size, shape, and degree of clumping of soil particles determine the number and volume of spaces for air and water within the soil. That's your porosity. Water can flow more easily through soils with more spaces than through soils with fewer spaces. And again, that's your permeability. All right, porosity, amount of airspace. Bigger soil size or particles will have more porosity and a higher permeability. Smaller soil sizes, right? Particles in the soil will have a lower permeability and a lower porosity as well. So definitely understand the difference between permeability and porosity and what it means for soil. All right, so how long might supplies of non-renewable mineral resources last? All right, so now we're going to head back. We talked about mineral resources. We now talked about soil resources. Now we're going to kind of circle back and begin talking about mineral resources once again. So non-renewable mineral resources exist in finite amounts. They can become economically depleted when it costs more than it is worth to find, extract, and process the remaining deposits. There are several ways to extend supplies of mineral resources. Methods, though, are limited by economic and environmental factors. So, we depend on a variety of non-renewable mineral resources. The first is something called ore. Ore contains profitable concentration of a mineral, and it could be high-grade or low-grade ore. We have metallic mineral resources, aluminum, steel, which is a mixture of iron and other elements, copper, gold, and something called molybdenum. All right, these are all examples of metallic mineral resources. So, moving on, some non-metallic mineral resources out there include sand, gravel, limestone, and phosphate. Okay, so definitely have an understanding of some of our mineral resources, metallic, and some of our non-metallic mineral resources. All right, so supplies of non-renewable mineral resources can be economically depleted. What does that mean? Well, first we need to learn a couple of terms. A reserve. Reserves are identified deposits from which we can extract the mineral profitably at current prices. So that's what we call a reserve. A gold reserve would be an area that we have enough gold there that we can extract the mineral and make money. It doesn't cost more money to extract the mineral than it actually would cost to sell that mineral on the open market, okay? Economic depletion occurs when extraction costs more than the remaining deposits are worth, okay? So that's important to understand. When the extraction costs more than the deposits are worth, we say it's economically depleted. It may not be environmentally depleted. There may still be gold down there, right? But the problem is it costs too much. It costs more to get the gold out than it would be to sell the gold. And so we say that that gold is now economically depleted in that reserve. Depletion time is the time to use a certain portion of reserves at a given rate of use, and usually that's 80%. So what does that mean? Once 80% of the reserves are gone, we're pretty much done, and we say that there is now economic depletion with that reserve because 80% of the ore or the metallic or the non-metallic mineral resource has been removed. So that's usually what we use as a guideline, that 80%, okay, time to use that 80% of the reserves at the given rate of use. Once 80% of the reserve has been extracted, then it no longer is profitable to do so, and we say we have reached the economic depletion of that mineral reserve. Options when a resource becomes economically depleted, well, we can do a couple of things. We can recycle or reuse existing supplies. We can try to waste less so that there's more of that resource available. We can use less. We could find a substitute, or we can just do without it. So these are the options that happen when a resource does become economically depleted. So what are we looking at here? We're looking at a chart of non-renewable mineral resources. Basically, there are three types of assumptions here. Assumption A is that we mine, use, and throw away. We don't have any new discoveries and prices rise. B there is recycle. It means we increase reserves by improved mining technology, higher prices, new discoveries. And then C, recycle, reuse, reduce consumption, increase reserves by improved mining technology, higher prices, and new discoveries. So what we're looking at are the curves from the depletion time to the production. So you'll notice if we're just going to mine, use it, and throw away, basically we're going to use the production, ramps up really quickly, right? And then just basically crashes. This is your 80% depletion time, these dotted lines here, right? So here you're going to be depleted very quickly. B, again, a little bit longer of a time here, right? You'll notice the 80% depletion time for B is definitely longer than it is for A. And then obviously for C, the depletion time here is the longest. So C is the best way to sustainably use a mineral resource, which is by recycling, reusing it, reducing its consumption, increase reserves by improved mining technology, higher prices, and new discoveries can help you keep the mineral resource not to become economically depleted as quick. So again, understand the differences between A, B, and C. Understand A is the worst, or we will get economically depleted the quickest, while C will be when we get economically depleted the longest amount of time. And obviously, when it comes to mineral resources, we want to stick closer to that C. We want to closer to the C range here rather than doing that A. All right, case study, the crucial importance of rare earth metals. So there are actually 17 rare earth metals out there that we are using widely in technologies that we have. So some products that are made with rare earth metals, LCD flat screens, compact fluorescents and LED light bulbs, solar cells, fiber optic cables, batteries, and motors for electric cars. So I would argue 50, 60, 70 years ago, we weren't using these rare earth metals. Now we are. And again, look at that word, rare. 17 rare earth metals, meaning there's not that many of them lying around. So again, just some examples for you. I'm not going to try to butcher a lot of these names, but you'll notice cerium in catalytic converters and batteries. You'll notice terbium here in electric motors and generators. Dysprospen is another rare earth metal, and here are just some more of you. So here are your rare earth metals. Definitely understand some of them here. I don't believe you're going to have to memorize these, but just understand that these rare earth metals are being used now in a lot of our newer technologies, and so may become issues with them becoming economically depleted as we go through this 21st century. So market prices affect supplies of mineral resources, right? Higher prices can do what? They can encourage the exploration for new deposits. They can stimulate development for better mining technologies. They can make it profitable to mine lower grade ores, which right now, lower grade ores not as profitable as higher grade ores, so maybe higher prices can make those lower grade ores more profitable. They can promote conservation, and they promote, unfortunately, theft. So that's one of the bad things that higher prices can do. But again, this is that full cost pricing that we've talked about, right? If you make the minerals cost what they actually do to the environment, it may drive people to do these other things, to explore for new deposits, to do better, get better mining, maybe deal with that lower grade ore, or just promote conservation. So things that can affect, obviously, the market price will affect the supply of those mineral resources. And we also have subsidies, tax breaks, and import tariff controls. They also control the supply, demand, and prices of key mineral resources. U.S. mining companies receive various subsidies to mine on certain lands, and again, that's something that may need to be stopped so that we can really get the full cost of what extracting these mineral resources are doing to the environment. So one of the ideas there was to expand reserves by mining lower grade ore. So factors that limit the mining of lower grade ores: first off, increased cost and energy to mine and process larger volumes of ore. So you got to, with the lower grade, you have to get so much more of it to make it profitable because it is such a low grade. So that's why it increases the cost and the energy. Also, availability of fresh water. So, right, you need fresh water to be able to mine efficiently. So if you don't have that fresh water, that could be an issue. An environmental impact of the land disruption, because again, for the lower grade ores, you need larger volumes. So you're going to have to dig or do strip mining, or more of the land will be disrupted when you're dealing with with mining lower grades ore because you need more of it. So what do we need to do? We need to improve our mining technology so that we can get to this lower grade ore and not have the issues that we just talked about. So one new thing is something called biomining, which is actually using microorganisms that actually go in, you put them into the rock, and they actually extract the mineral from the rock, these microorganisms. But unfortunately, it's a very slow process, but that's something that the technology just starting in the last 10 to 20 years, so maybe this could be something you get into, right? Trying to figure out how to quicken up the pace of this biomining, because again, biomining has shown that it could be a low cost and very effective way to deal with getting more of that low grade ore, which again would just expand our amount of mineral resources. We can also get more minerals from the ocean. Right? Mineral resources are dissolved in the ocean in lower concentrations, but they are dissolved in ocean water. In addition, deposits of minerals and sediments along the shallow continental shelf and near shorelines, we may be able to extract them. In addition, hydrothermal ore deposits. We have hot water vents on the ocean floor known as hydrothermal vents that actually have ore deposits near the vents. So maybe we can go down there and mine those hydrothermal vents. Metals from the ocean floor like manganese nodules, right? Can we get them out? And what is the effect of mining on aquatic life? We don't really know because we haven't really done this yet, but something that to think about. And again, as you guys move out into the workforce, if you happen to get into this type of environmental business, this could be something where you figure out how we can get these mineral resources from the ocean in an economically and ecologically friendly way, and then this would, in addition, would increase the mineral resources that we have. So here is just a picture of a hydrothermal deposit. Again, these are these hot vents at the bottom of the ocean. Not only do they have a lot of organisms, tube worms, white clams that live around them, but sulfide deposits and again, other type of mineral resources are deposited here and potentially could be extracted for human use. All right, so I'm going to end part 1 there. Again, part 1 of chapter 11, Geology, Soil, and Mineral Resources. Make sure to check back in for part 2. And as always, thanks for listening.